other questions for him. Okay, so now it's time to maybe we stop. Okay, do you want to continue stop sharing? Yeah. And Begoña, please, if you want, you can start sharing your screen. So our last speaker, our next speaker, sorry, according to the program is Dr. Begoña Ferrari, that I have the pleasure to present to you. I know Begoña for a while, and we have a couple of activities in common, and we share, I would say, scientific passion for similar topics like shaping and additive manufacturing and electrophoretic deposition, etc. So Dr. Begoña Ferrari leads the research group tailoring through colloidal processing at the Institute of Ceramic and Glass of the Spanish Research Council, and she's co-founder of the CSIC spin-off called Feed for Printing, that, by the way, is one of the companies that will share experience with us tomorrow. So I'm really calling your attention that we are going to have very interesting presentations coming from the companies. She's the current General Secretary of the Spanish Ceramic and Glass Society and member of the Council of ICERS, and was his expert for different national and international evaluation programs. She was his leading of national and international research projects and industrial contracts, today focus on the innovation path that the integration of the colloidal chemistry and ink suspensions technique provided to additive manufacturing of ceramics and composites. So Begoña, thank you very much for being here and accepting this invitation. It will be a pleasure to listen to you. The floor is yours. Thank you.
Thank you very much, Paula. You can listen to me correctly, yeah? Okay, perfect, great. Because I am going to put here, I don't know if, yeah. Okay, disappears that, okay. You can see yourself.
Yeah,
right?
we can see your slides. So you are sharing, yeah.
Yeah. Okay, great. So in this moment, I cannot see all of you, but I want. It's quite complicated that for online presentations. So thank you very much, Paula, for your invitation. It's really a pleasure for me to be here. Present this nice subject about and talk about 1 hour, 50 minutes about additive manufacturing of ceramics. That's true that ceramic is my field, right? But it's true also that today is quite complicated to talk about ceramics and don't talk about polymers and metals, and you are gonna see along the conference, the little presentation that this is true, right? So to start the presentation, yeah, only to show you where we am in the Institute of Ceramic and Glass here in Madrid, in the north of the city, right? You can see here the skyline and the building of the institute, and you are really welcome if you pass through Madrid. That is not difficult to visit us if you are interested to see all our facilities, right? So I'm going to show you here the map of the patent in additive manufacturing and in additive manufacturing of ceramics. As Andreas saw few minutes ago, the patents are really for additive manufacturing is really old, right? And also some of the this manufacturing technique has been patented for ceramics around the 90s to the 2000, right? So we are not talking about so emerging technology because the patents are old. But this is true that industrialization is coming from the last years, right? So it's very important the concept of additive manufacturing because, sorry, okay, because it's not new at all. You are going to see that we have many processes that give us the knowledge, enough knowledge to be here right now, right? So additive manufacturing of ceramic has two kinds, big group. One of them is the indirect additive manufacturing. That means that we print a clean body that we need to sinterize, right? And another one is to create directly the final piece. In my opinion, any one of them is the best. It's like processing, right? Any kind of process can be considered the right process. The question is, what do you want to process? To have one microstructure, you want to have a sample, you want to have a composition, you want to have a shape. So you need to look for the best processing, and in additive manufacturing of ceramics is exactly the same. The main processes involved in this little schema of the additive manufacturing is process like granulation or like engineering and modeling, and also non-conventional sintering. I think in these three fields we are working a lot to put the additive manufacturing in the companies to use it industrially, right? Let me show you on the first time a little difference between the metal processing and ceramic processing, right? Because additive manufacturing for metal and ceramic is mainly a powder processing. So it's very important to know that when we are processing metal, we are processing high side powder. That means we are working with more than 70 microns. Also, this powder usually you need to have a high shape factor. That means these particles are ductile. So when you press them, they can move, right? They can change their shape. And this is why we, in powder metallurgy, we can achieve 85% of density before sintering, right? That is very, very important. Because if you go to ceramic processing, pressing is not exactly the same. Most of the time in technical ceramic, we are working with low side particles. That means we are working in the micrometric or submicrometric size. We are working with spherical particles, hopefully. That means when we have huge factors of shape of the particles, so it's quite complicated for us. And our particle is hard. So that means that when we arrive to the compaction process, we are in the 72% of density before sintering if we are lucky, right? So this difference make really the difference between the additive manufacturing techniques that we use for ceramic and we use for metal, right? This is the big differences between the particles, difference between the particles. And also because ceramics right now, we can work in technical way and develop this fashion structure and microstructure, but also ceramic are used in combination of metal, and this is quite complicated to produce by additive manufacturing, right? But so it's really a challenge to make ceramic and composite with this technique, but the benefits are great. We can have any kind of shape in a low cost, right? Without molds. So this is really important for us. Another thing that is mandatory to say in ceramic is that we work most of the time with nanoparticles right now, right? What that means, when I started the thesis a long time ago, I call my zirconia like submicron particles, and today the same zirconia is called nanopowder, right? Why? Because we work below 1 micron, right? And most of the time, and sometimes below 100 nanometers. That means that we have a lot of particles in our batch, and also we must deal with a huge specific surface area, right? And also imagine, because we love this kind of material that I saw you here. We love to work with nanostructural material, for example, to improve mechanical properties, or to improve catalysis, or to improve lithium exchange, right? So we need to work with 0D, 1D, 2D, and 3D materials. So in ceramic, it's really basic to have a tool to process this kind of particles. And well, what we do in ceramics that we need to reproduce by additive manufacturing techniques. We can synthesize a B3 oxide. We can work with small nanocrystals. We can work with this 2D, 3D nanostructure, but also we need to organize all this particle in different kind of microstructure, right? To disperse phases, to make granules, to make laminates of functional graded materials, to make multiporous structure, and also to make thin and thick coatings. So we have a lot of tasks to do and to research and to invent in additive manufacturing in the ceramic field, to manipulate the crystallography, the morphology, and the microstructural characteristic of our material. I give you here an idea of 4 of the most common ways to shape, to compact powder. That is very known, I think, from all the people that work in ceramic, has been working in filtration, or knows what means flocculation and coagulation, and also has used gels and used thermal pressing, and also knows what is dipping or spinning or plate casting or electrospinning, right? I think all this kind of processing are very standard, right? And all of them has a lack. If you compare with additive manufacturing, is the mold, right? We need to fabricate the mold to have a shape. This is that the additive manufacturing technology is changing completely. We are doing materials in a layer by layer manner, and this processing is commanded by the computer in a rapid prototyping process. So in this sense, you can design whatever you want. And the thing is how to provide the machine with this nice powder or inks or suspension to produce this customized shape. So for that, what we use a lot of plastics, right? Really, organic moleculars and polymers are in the life of ceramics for a long time ago. And right now we are using more and more organic moleculars and polymers in all the steps of the production of ceramic material, right? For synthesis, we use catalyzers, site modifiers, and stabilizers. But to adjust rheology and to produce material, we use also binders and plasticizers, gels, templates, or ceramic precursors. So all these polymers are very important raw material for additive manufacturing in ceramics, because if we don't have them, we are not going to produce the ceramic correctly, and we are not achieving to have dense material and compact and dense material at the end of the thermal process. So all these properties, chemical one, thermal one, rheological one, optical one, and flow one of polymers are very important in the world of ceramics, right? And also the way we manage, we are able to mix this polymer with inorganic particles, with ceramic particles, is also important. This is why in additive manufacturing start to learn about the colloidal materials, right? It's very important work, and you can see in this review, it's very nice how this colloidal chemistry is operating in 3D printing technologies. In fact, when I was young, everybody speak about slurries or suspension, and right now all people working in colloidal processing speaking about inks, because inks is the suspension that we need for additive manufacturing techniques. So what we do, we need to mix to stabilize the powder. We need to dissolve the polymers. We need to mix them together, and we need to have a granule that have the composition, the binders, and the inorganic particle there. Or maybe we go directly with this bed technologies to shaping, right? So to mix them in wet or in dry is very important step for additive manufacturing, because we need the polymers. This is the more famous, I think, slide that everybody saws, that is summarizing all the technologies that we are working with. We are working with them also in ceramic. I think Andrea made a very nice presentation of all of them and how we work with them, right? But the thing that we want to make is a separation between two kinds of groups. This one here, we need paste, ink, and slurries to use it. And this one, finally, we need composite granules. We need polymers, binders, plasticiers, and inorganic particles in our material, right? The first one of the additive manufacture processes that I want to show you today, some results in ceramics, is this laser additive manufacturing. We have many techniques in this sense, because depending on how we apply the laser, we have direct energy deposition, stereolithography, that we use inks, indirect powder bed fusion, and direct powder bed fusion or sintering. And even in this case, we are now using filaments for that, right? What happens with this technology? In this technology, are based in the sintering of melting of inorganic particles by the action of a laser. You can imagine that you are using light, so you have a pixel resolution, right? And it's a very fast technique to produce material, but it's very expensive. Why? It's very expensive because you use a bed of powder. That means you have a lot of waste in this material. So people are very interested and also are very worried about how to use this bed, how much time we can use this powder in the bed and reuse them to make the final product, right? For that, in the last few years, there are another technology that is very, very relevant, and is this one that direct powder fusion, bed fusion, but focalizes in one point, right? So in this sense, you are putting the powder at the same time that you are applying the laser. So it's not exactly a powder bed, it's another kind of system that give you some problems also, like is to solve in this moment, that is the porosity that is very poor, and you cannot densify very well. You can have different kind of problems with the microstructure, because you are playing with grain size, grain boundaries, and phase transformation in the same time, and also in a non-conventional way, applying a very energetic focus light, right? And you also are changing the mechanical properties and of your sintered body, and you can produce cracks and microstructure. And also at the end, you have problem with the defect stresses developing by this thermal induced shaping process, but also the surface can be no good quality. So with all these problems, you are going to ask me why we need to research in this process. This is very easy to answer. If I show you a conventional slip casting material made in aluminum zirconia, this publication is in the 98, right? You can see here all your alumina grains and here all your zirconia grains mixed together in a laminate. And if you go to the direct lesson additive manufacturing, you are going to see exactly the same material, 40% zirconia here, but in a completely different microstructure. So like non-conventional technologies, this direct powder bed sintering is really a very powerful technology to discover new material, right? It's really hard, it's really challenging, but is really, we have a lot of expectative in this production, because we can develop different kind of microstructure that we cannot achieve in another way. In binder jetting, this is the other technology that we use in ceramic with powder and granules in a bed. In this technology, we are using a printer head that eject the binder, right? This is very fast technology because jetting is industrialized and very fast technology. We have a lot of machines working in this with this kind of jetting head. And this technology is based on binders, right? So that means again in polymers, right? Here it's very important to have a powder with high compressibility and high fluency, right? In this review, you can see this nice graphic here that show you the powder density during the time you are measuring the apparent density in the bed. And when you tap this powder, right, is the red one. And when you are promoting or forming or shaping the green part, right? And you are going to see that when we tap, that means when we try to improve this fluency of this, try to compact by tapping this powder, we have the huge density in green, right? Even better that when you put polymer in. So what means that? That means that we need to improve the fluency of this powder. And the problem in ceramic is we work with very small powder. Remember my slides, my previous slide related to metal and ceramic powder. We use a very small powder, and this small powder has not enough fluency to be packed, right, when we put in the roller. So we need to improve this fluency, right? Of course, this technology has a conventional thermal treatment after you have your part, and the amount of binder is very important here because you must make the binder process during the thermal sintering, right? So the problem of this binder is creating these large porosities in the pieces that we need to avoid increasing the characteristic of the properties of powder, right? And one way to improve in both technologies the characteristic of this powder is to make granules, right? to make granules, to make that this small amount, small particles here becomes a bigger one, and fluidity of these particles increase with the size of the granules that you put in the bed, right? Granulation is a very old technique to make many things, right? You can make dense particles, hollow particles, smart particle, core cell, encapsulate particles. You can make whatever you want by granulation. In this case, we are talking about to mix two materials, maybe an inorganic particle and a polymer together, to mix together and to achieve a very dense material to put in the bed of binder jetting machine, or maybe in power bed technology, right? So this spray drying technology is well known in ceramic. In the ceramic industry, everybody uses it. So we can prepare the suspension, mix together all the powder with your polymer, and in a drying room, you can make this kind of granules, right? It's very important to have a good suspension. Doesn't matter what kind of inorganic particle you are going to use and what kind of particle size or morphology of this particle. And at the end, you are going to have these nice granules that you can manage inside morphology and composition, right? And in the camera, you can work in different kind of atmosphere, temperature, even under 0 degrees, that means doing freeze drying or in vacuum, right? So you have many possibilities to have or to perform this kind of granules that you can use in additive manufacturing to make more compatible the phases, increase the fluidity of the powder, and also with the fluidity, the compressibility of the powder, right? So this is an important thing that we, people that devoted to colloidal processing, used to use, right? So we need to passivate the suspension. We need to be sure that our surface is good, is surviving water, right? And also if we are using trioxide, this combination of metal inside of oxide that give us so much application and functionality of our materials and composition should be there, right? Metals cannot go out, cannot dissolve, right? So particles should be modified in the surface and prevent dissolution of the particle or the exudation of the cations. So we must to promote the chemical stability and colloidal stability or particles. And finally, another thing that is very important stuff is to manage the rheology of our particles, trying to promote different kind of behavior of polymers that we use to preserve the composition of the particles in water, try to decrease in the way that we can the hydrodynamic diameter of our particle and individualize the particle, because our final end, the objective is to have a high packing degree of our particles, right? And this is very important also to granulate. We need to have full dense granules to make work the spindle jetting and bed process, right? So also in granules, you can manage with different granules with different sizes. You see here titanium surrounding by alumina, or even you can play with the particles with similar phases, similar sizes, right? And also you can incorporate to a big granule some nanophases by synthesis, right? In this way, you are preparing the feedstock of your additive manufacturing technique, just to have a very coherent microstructure at the end of your work when you arrive to the sintering, right? And have all the two phases. In this case, is a titanium carbonitride and iron nickel alloy here mixing together, and to have a well compacted microstructure that work very well in this 99 days ferment, right? So this is an important thing for composite granule, but what happens in ceramic when we use ink or slurries of paste in the other technology? Well, I saw here, I think 4 of the most used technologies, right? Here, the robocasting and direct writing, that is a material extrusion technology that is different because in robocasting we use pastes, and in direct writing we use inks, right? Liquid inks. And it's very important to study stabilization and the rheology, but also the gelling is quite important in this technology, specifically in direct writing. We have fusion filament fabrication. It's also a material extrusion processing, right? And also we need to stabilize and study the rheology of the suspension and the suspension in the melt thermoplastic that we use to promote or to print or filament, right? And also we have this digital like processing or stereolithography. Here we use inks with low rheology, and we need to take care about the curing process or monomers with light, okay? And also we have this inject printing that we are using liquid inks, most of them of Newtonian behavior. We need to tune the surface of the particle, the stabilization of the rheology, and it's very important because this is a 2D process. How is the ink wettability with the substrate you are going to put your ink, your material in, right? So there's 3 groups of processes in ceramic should be described a little more in detail. Here you have in the material jetting, right, technology. This is the inject printing. And here you can see that we use a piezo element to promote the formation of some goods, right, in a head that have many of this nozzle that you can see here, and you are promoting the formation of a design, right, a pattern. You are using here very small particles. You are writing in lines here. This is a really expensive equipment that we are using here, but we can use with many materials in the same head, right? And we need a post-treatment. And if you think that this is a dream, it's not true, because we know a lot about inject printing, and this is real an industrialized process that we use to make all these tiles that we have at home, right? So this is a printed head that the industrial machines use to print in this machine that you see here, right? And you have more information in this YouTube description, a little seminar, right? And in material jetting, in this way, printing inks with glasses in, you can have all this kind of nice design imitating many shapes of a stone or different kind of pictures or whatever, and you can make your picture yourself in your tile and putting them in your room, right? Because it's working like photocopy, right? It's exactly the same. There are a lot of technology in. Is very relevant for us in functional materials, because when we go to the nanoparticles, right, we can promote the printing of these inks, and we need this nice review of Professor Derby explained very well what is the printable region of these inks. We need a very relevant ink requirements related to the particle side with the nozzle related to the nasal radius, also the surface tension of the ink, the viscosity that I told you that should be Newtonian to maintain and to start to eject, to flow, right? The density is very important because it's a process where we only have evaporation, like a process to evaporate, to take out the solvent, right? And also, of course, the pH of the suspension, because we are using most of the time metals in our equipment, right? So this is the requirements, join the printer parameters, that is also very complicated to adjust to have a continuous printing, right? This challenging process can give you this kind of patterns that I saw here in this video, and you can manage whatever you want with a CAD design. And you are going to have this kind of a structure here, you see, and your nice little particles. This is nanoplatelets on nickel oxide, right? You can build one layer or two layers or whatever, and you are increasing the height of your pattern, okay, layer by layer. But honestly, this kind of additive manufacturing technology is only for patterns right now, right? There are not any self-supporter pieces that you can have from this kind of process, right? But if you can put them in tiles, why not? You can put this kind of materials in any part, right? To build more sophisticated devices like photovoltaic, for example, right? And the second process that I am going to comment here in ceramics is the photopolymerization, right? The way you focus the laser or the light is given many kinds of processing technique, right? And the more relevant thing is the accuracy you have in the design, right? In the final piece. This photopolymerization process is very interesting, has a very interesting resolution, right? But we must take care, because it's of course a pixel resolution, but it depends on the particle to use. This pixel resolution can be larger or shorter, right? You must to think about where you are focusing the light, right? It's very fast, but it's expensive, and also have a lot of waste to take care of them, right? As I told you, you can have many problems with the scattering, for example, the light, depending of the kind of distribution of particle distribution you have in your suspension in your bag, right? And also you must take care of the slurry. Each time that we put particles in the monomers dissolution that we use for photopolymerization, we must to take care about how high is the viscosity, right? Because if not, you cannot perform correctly the piece, right? Here I show you an example that we do in the lab. You can see here a correct piece where you can see that all the holes have not suspension in, right? And you can see here if you are doing or using a very high concentrated suspension, in this case is hydroxyapatite. You can see here that you can have problem during drying and even during the shaping of the material, right? So anyway, we can adjust the rheology, and we can even make this kind of pieces that it's so small, is the bond that we have in the hair, and we can sinterize this material this is hydroxyapatite, so in a porous way, right? And we can perform this kind of material that we cannot achieve in another technique, right? Because it's a really accurate prototype of material. The problem of this material is really to make them fast, right? And also to manage the working zone that we have in the suspension, right? To manage the relation between the working zone when the light is working, right, and the dead zone that is surrounding this part of the ink, right? And really there are a very good line of based on preceramic used like raw material in this technology, right? This continuous direct light processing technology is really new. You see here is from 2021, right, paper. And here you build your material inside of the ink with managing this working zone and dead zone and using preceramic as raw material. And you must take care of printing speed and energy intensity, because both of them is gonna describe or define the thickness of your design, right? So I want to show you, I think it's this one, right? Oh, it's working, it's not working. Oh, okay. So this is the way that people build this kind of material, but photopolymerization, working a lot to maintain this to some in a correct ratio to print, right? So the last one is the material extrusion. There are many technologies based on the extrusion of material. Here you have the robocasting, you have a paste here like a feedstock. In ceramic, you have indirect writing the ink, liquid ink, most of the time managed by the inclusion of gels, right? And here you have also filament fabrication, that we use a filament with thermoplastic, introducing the inorganic particles in a thermoplastic polymer. And here I think that polymers are the key, right? Because if you don't use the correct polymers in this feedstock, you are not going to process the ceramic material, right? So this technique has not so good resolution that the other one, but it's very important in the industry sector for prototyping, right? Here I saw you two machines. One of them is the robocasting and the other one is the direct writing. You can see the difference in the machine, and you can see this is the difference in prices. Robocasting is pressing paste, so you need a lot of pressing in, and direct writing you are pressing ink, so the pressure is not so high. Here we left all the work to the chemistry of the ink that should work for you, because should gel by the time that pass to the nozzle to maintain the next layer, right? So it's very hard work to work with this gelling inks, right? Here there are a lot of development in biomaterial, right? You can see many places where you go, there's noses and ears that you can perform by using gels, right? And I'm going to put an example of how we work with these inks in also a little paper, very new paper in 2021 is published, right? So here you put Boemit inside of your gel and you print by direct printing, and you must to take care of drying to have the final piece, right? And what we look for here, we look for the share rate that you promote through to the suspension, to the ink, when the ink is passing through the nozzle, right? It's a very important thing to have this kind of viscosity, not too high, not too low viscosity, right? To make that the ink pass through the nozzle with light pressure in your surgeon, right? That you use to print. But also it's very important to know how this ink is passing through the solid state, right? How stable is the solid state that you have with this, with the gel that you include inside of the ink. Here you can see different suspension and different modulars. You can see this the solid state of the described by the G modulus is increasing with the stress when you increase the amount of particles inside of the suspension, right? That this is good because when you pass through the nozzle quickly, the ink becomes gel, and also it's very important the amount of gel that you use in the ink, because as much as you use, you can enlarge this point, this behavior of stability of the solid, of the gel in your suspension, right? So this is the images of the particle, of the pieces that we can have with this kind of processing. And also this technology, the study of the rheology of the suspension make us to describe the force that we can use to print or to have this kind of patterns of design of 3D pieces, right? And finally, the last processing technology that I want to show you is the thermal one. Here we are using thermoplastic polymers to build this kind of filament, right? We have inside of the filament, we have inorganic particles. And this technology is based in the thermoplastic melting. You know, when you pass it through the nozzle, you have warm the filament, and you create layer by layer your 3-part, okay? And we use this kind of granulation. We prepare the suspension and mix. So you, in the beginning of the talk, we have these granules, and with these granules, we prepare this kind of filament. You see here the granules in a small extrusion we use in the lab, right? That has not too huge thorn. We have a hot thorn of 15 centimeters, and we work around 155, 175 degrees C here, and you are going to see that we are able to promote, to make this kind of filaments and prepare them for printing, right? So you can introduce in this filament whatever particle you want, right? And this is the filament. This is our 3D parts, some scaffolds. You can see here how we print, and you can see here how is the particles isolated and mixed with the thermoplastic. We need to take care of a thermal characteristic of our filaments, because by the time we are increasing the amount of particles in the filament, in this case it's also hydroxyapatite, we are decreasing the temperature of degradation. So the filament is degrading faster, right? And also we need to take care of the viscoelastic behavior of the melting, of the melt polymer with the particles inside. It's very important. You see that the rheology is not exactly the same that the gelling one. Is more strange rheology, right? You must define how much viscosity you have there. It's huge, the viscosity here. And also you need to know when this filament is passing through the solid to the liquid part, and also to the solid again, right? So you need to study very well this rheology. Here you see the printing technology, how it's working, and take a view of this micrograph that is here. That you can see the little particles of hydroxyapatite surrounding completely from the PLA, right? And this is the kind of filament that we are printing here, and you can see here two pieces, right? It's very hard the binding of thermoplastic is really hard, right? You must take care of melting point of this thermoplastic, but you can arrive perfectly, and you can have a completely inorganic macrostructure here. So this is my final slide. I think that I convinced you during all my talk that ceramics needs more than ever the polymers inside, right? We must work with polymers and organic molecules, because this material is really the vehicle of printing, right? And we need them to produce ceramic materials in a correct way by additive manufacturing, right? And I think the talk of this evening or after lunch is gonna be very interesting, related with polymers, right? Or maybe tomorrow, I don't remember exactly what is the talk. And at the end, well, I want to thank all my team here that give me the possibility to talk with you and give you all this example that we made in the lab, and also all this that I saw you of many processing technology collected by the literature, right? And of course the project that found all this research. So thank you very much. I don't know if it's time or it's more than time. Paula?
Begoña, yes, it's more than time. Thank you very much.
I'm sorry.
No worries, no worries. We will also, we still have a little bit of time, because we are going to make a break now for half an hour, and then we come back. So that's why I was not interrupting you, because this is and was a very interesting talk. Thank you very much, Begoña. So now, please raise your hand or ask a question. Let's start to discuss and commenting what Dr. Begoña just presented to us. Very shy, this audience, Begoña, very shy.
A lot of information altogether.
Okay, Andrea, please go ahead.
Yeah, thank you, Begoña, for a very nice presentation. You know, this is my main topic as well, so I enjoyed it really a lot. I have a question about binder jetting and what you mentioned, granulation for binder jetting.
Yes.
We also have some experience on this, and granulation improves flowability of the powder, so this can be very a really important advantage for the processing. But on the other hand, we experience with granulation a lot of issues because the microstructure, so the distribution basically in the powder bed is not homogeneous, which creates problems both during printing for the distribution of the binder and also for sintering, because the material doesn't sinter homogeneously in most cases. Do you have any tricks or suggestions maybe to improve these problems?
You know, that is really complicated because you have two kind of binders here. You must play with binders to make the granule, right? And most of the people is working right now to mixing in dry, right? Like pressing. People use binders that we use regularly by pressing, right?
Yes.
Press powder, right? You have this kind of material, more or less, right? More or less. And to move to this material that gives you better fluidity, you must go to a spread dry or freezing, right? And well, I can tell you that for pressing is working very well.
Yeah.
Because you are increasing the size of the powder, and fluency here is really, really important stuff, right?
Yeah, this is exactly what we also experience, that pressing is a bit different, because in pressing you're crushing the granules, so you are obtaining a more or less homogeneous microstructure again. The problem in binder jetting is that the distribution in the powder bed remains inhomogeneous in our experience.
Yeah, but in powder metallurgy, we have some experience there, and fluency is very important to fulfill the mold, right? Mm-hmm. You need to put all them by the time that you are making the piece before pressing, you need to fill the mold, right? And fluidity in this case is really important. It's very important to have the apparent density and the tap density to close, right? Mm-hmm. Even in pressing, even when you have pressing later, right? You must press, right? And here I agree with you that we are not pressing at all the piece, but the fluency of the ceramic powder is very bad. It's really, really bad.
Yeah, we know that. It's a big problem, of course.
We work with small particles, right? We work yes. 1 micron, 10 micron. This is nothing. Think that people in metal is working 100 microns. This is fluency. They have fluency. We don't have nothing. Okay, so this is a problem for us, really. So by this time, most of the people that is working with this feedstock is working with that, right? With this kind of feedstock, no working with granules and spray drying. But I think spray drying is gonna be a nice way to perform this feedstock. We must to look for.
Okay, thank you.
Any other questions? 2 participants raised their hand. Very good. So, Rafael Matheus, please go ahead.
Hi, hello.
Hello.
Good morning. I arrived a little bit late, but for what I understood, you just referred the material jetting for patterns, not for solid parts.
Begoña?
Yeah, that's true. Most of the material that we perform with material jetting, with inject printing, right? No binder jetting, okay? Inks jetting, right? Is for patterns, right? This machine that I saw you here is for flat substrates, right? You can imagine here the tile is passing through, right? It's a flat substrate. It's quite complicated to design this kind of machines of equipment to cover, to make patterns in a substrate with some shape, right? It's only for flat substrates right now, right?
Okay, I'm asking it. I think I arrived a little bit late, but we have X-Jet here. And I don't know if you know the technology, of course.
Yep.
Okay, that's why, because what?
This technology, inject printing.
X-Jet. They printed by jetting material, ink.
Yeah.
Yes.
Alumia or zirconia, and that's why I asked, because I know that we can print dense parts with jetting material.
Well, this is a specific. This inject printing is a very specific technology, right? It's really industrialized, but maybe you have another kind of technology, because there are many.
Okay.
This is the more standard one, right? Okay. And I tell you something that is not true, because I think that there are a company. I think it's Crayet. It's a company that is building this kind of machines to make designs pattern in volume, right? But it's not really a 3-part. They are able to print in volume, but it's not jetting with piezoelectric, right? And jetting inks. Maybe you have another kind of jetting process, right? Because you see here, binder jetting is more or less the same kind of machines, right? but it's jetting only binders, right? It's not jetting the ink. So independent of the feedstock and independent of the technology of the equipment is providing this feedstock, you have a different kind of processing, right?
Okay, thank you.
Begoña, there's a question in the chat from Mateus Moraes. Thank you, Rafael. Which of these ceramic IM process do you consider most suited for dense parts with a high mechanical properties?
Well, I think
tough questions, yeah.
I think the most evolved process right now is robocasting, right? In my opinion, it's not the best, but right now it's the more evolved one, right? Why? Because it's the first one that they start to build this kind of structural materials, right? It's coming from technology related to injection molding in the machine, right? You are applying huge pressure. But I think that we can achieve this kind of density if we work very hard in binder jetting also and in direct writing, right? We push more effort in our composition, right? That's in the machine. I know if you understand me, Paula.
Yes.
More important is for example, it's really important to think about the composition. In ceramic, we use a lot of nanoparticles. So robocasting, you cannot make paste with a high enough amount of nanoparticles to have a dense part, right? So we must put some emphasis in the feedstock. We mix in dry or we mix in wet, doesn't matter. But we need to study that to improve our materials and play with and join the advances of the engineering people making the equipments, right? So robocasting right now, I think is the most involved. Okay, and I think also that maybe fused filament, why not? Direct writing and binder jetting are the best right now.
Yeah, Begoña, thank you very much. I think this is a very interesting discussion. I just have a comment here that I think that is relevant. One of the interesting parts of these discussions and these questions, for some of these questions, we still don't have answers. But however, this hybridization of technologies may lead to a particular one. So in my opinion and my experience, there is not one technique that we say, oh, this one is going to be the best. There's a lot of considerations we should make. And maybe some companies should have more than one technology, depending on the product or part they want to print. So I think that currently it's very difficult to say this is going to be the technology. However, there's a comment, Begoña, that you made that I think is relevant for the companies. Some companies are here with us, so they have already process installed as the one of atomization or spray drying, right? So it's a very common, normal process in the companies.
Yeah, that's
so I think that's a good point, you know. So they are also used to do slip casting, I know, but in terms of spray drying, it's really a very powerful technique. And according to my knowledge, there are not that many people paying attention to use the spray drying to prepare the powders for all of the powders printing techniques. Yeah. And I think that's a very nice point that you made. I already registered, so when I will do the sum up of this workshop, I will put this point as one key relevant aspect.
It's a really traditional way to make granules, right?
Absolutely.
That's, it's fantastic.
Yeah, I think so. And I think when you want to produce tons of powders, this is although energetically it's an expensive process, it's a process that the companies are very familiar with. So I think here the work together with those that fabricate equipment, together with those that use the equipment, and eventually with the scientists will be the correct partnership to go further with these techniques. That's my feeling. Begoña, it was very nice to listen to you. It's a pleasure. I invite you to keep staying with us. I'm expecting the talk of tomorrow about the filaments that you are producing with your collaborators. It's going to be very interesting. So please stay around. Thank you very much.
Thank you, Paula.
To everybody, we are going to make a break until 11:30. At 11:30, we come back with Dr. Klaus Kopp, that is going to talk about metal binder jetting as a supplement to beam melting. And the chairperson will be Professor Jorge Lino. So we will meet in approximately 20 minutes. And please note that we are on West Eastern time. So we are at this moment in Portugal, London and Dublin, 11:13. Okay, so see you soon. Thank you very much. Bye. Então, quantos é que nós estamos agora? Dear Dr. Klaus Kopp, thank you very much for being here.
Yes, now I can hear you. Perfect.
How are you?
I'm fine, thank you. How are you?
Very good, thank you. I think
Okay.
we started very well. We started very
Okay.
well with a very nice number of participants, and I think we will continue. So we still have 2 minutes.
Okay.
We are running on the West Eastern time, so we are running on London, Lisbon, and Dublin time. So this morning there was a little bit of I put an announcement saying this is the WET, not Central Eastern time. But okay, no problems. So thank you very much for being here. It's a pleasure to have you here. I think this is a very important thematic now, and sharing this knowledge with the people that is doing research development is really very important. So thank you.
Yeah. Okay.
So just to inform you that the chair of your session, it's going to be a colleague of mine. He's Professor Jorge Lino. Are you there? He was here with us this morning, so I think he will join us quickly.
I'm here.
Yes. So
yes.
Professor Jorge Lino is also a professor at the University of Porto. And he's a material scientist, and he's a professor very involved in additive manufacturing in Portugal, with a lot of collaborations with the companies. So I invite Professor Lino to join us and to share your session, because you have common language. So Jorge and Klaus, the floor is yours. Okay.
Okay, Klaus, thank you very much for coming and attending and do the presentation in this event that Paula prepared for a long time, and also with the enrollment of the Portuguese Society of Materials. So it is a big pleasure to have you here with us. Talking about AM of metals. In fact, metals are a big challenge for AM because of the high melting temperatures, and so I think that we have for a long time this world of additive manufacturing manipulated by the polymers, because are more easily processable. But this last decade is characterized by a great increment and great growing of additive manufacturing of metals. So I think there's obviously metals are a group of challenging materials because of the mechanical properties that they present. And so people have been, more and more people have been enrolled with these studies and also applications of metals in different areas with all the challenge that this represents. So machines are very expensive, metallic powders are very expensive, so we need to optimize all of these, not only powders but also metals. So we are very curious about your presentation today and your point of view and about the future for this technology. So thank you very much once again, and the floor is yours.
Okay. First of all, you can hear me loud and clear, I hope?
Yes.
Okay. So I will share my screen. And
we are not seeing you.
Yeah, I just lost the camera and can't reactivate it. I don't know if the host can do that.
Your camera. Okay, let me try. I can do several things. Ask to start the video. I've asked you to start the video.
Yes. I have confirmed, but nothing happens. Can I share my screen? You
Yes,
don't
yes, yeah.
You can, yes.
Yes, of course. Please try.
Okay. So can you now?
Yes, yeah. Now we can see you and we can see your screen.
So 2 in 1.
Okay.
Oh.
Yeah.
Okay. Okay. Can you see my mouse moving on the screen?
No.
No.
That we cannot. You have to activate the pointer.
Yeah. Curious. Oh. But you see the first slide with the 2 pictures.
Yes.
Okay.
Yeah.
Okay. That's great. I think so. So thanks again for having me in this workshop. And you were talking of metal AM in general. In my talk, I will concentrate on metal binder jetting as a supplement to beam melting. So 2 of the most discussed technologies at the moment, I think. And the reason is also that we have been concentrating a lot on binder jetting meanwhile, since beam melting technologies are well known, are well represented in the market. And I just wanted to inform the public on this new approach or reborn approach of metal binder jetting. So a short introduction into the institute where I'm from. Some general remarks on what we do at the institute. And then I will go into details on the metal binder jetting process, the metal binder jetting market, and the usual conclusions. So I'm from Fraunhofer IFAM. The Fraunhofer IFAM is part of the Fraunhofer Gesellschaft, Fraunhofer Society, which is Europe's biggest research institution, and has meanwhile or consists of 75 institutes all over Germany, and those marked with numbers here on the map are belonging to my institute. The whole society has about 29,000 employees meanwhile, and works with an R&D volume of 2.8 billion meanwhile. My institute itself is headquartered in Bremen, so northern Germany, here where the 1 is. We also have further locations in Dresden. For historical reasons, we have about 120 colleagues in Dresden. We are also present in front of some of our major customers like Airbus Industries here next to Hamburg, a small city called Stade. We are with a big automotive OEM next to Wolfsburg and Braunschweig, which is Volkswagen, of course. And we also have a site at the island of Helgoland in the northern sea area, where we do special tests for seawater life of materials and seawater behavior of materials. Our institute, or my institute, has about 700 employees and a total budget of about 60 million. We are located here in Bremen, very close to Bremen University. On the picture on the left, you can see the campus of Bremen University with the famous drop tower on the upper left. And our institute is located in the area with the red rectangle marked here. And we have been working with metal powders for, let's say, 4 decades meanwhile. So more than 40 years of experience with metal powders. We are dealing with technologies like powder compaction, metal injection molding, and from beginning in the early 1990s already with additive manufacturing technologies like laser beam melting or laser powder bed fusion, as you may call it today, and some other metal powder based technologies. We have a broad variety of systems available in the institute, ranging from powder bed fusion, laser-based, powder bed fusion, electron beam-based, where the devices are located in Dresden. We are running 4 metal binder jetting systems. Meanwhile, also in Dresden, we do something called 3D screen printing, also a metal powder-based 3D printing technology. We are looking into fused filament fabrication, new technologies like mold jetting, gel casting, lithography-based technologies like the newly invented LMM technology. And all is connected via metal powder quality testing things. So we have accredited labs. Excuse me? Any remarks from your side? No. Okay. Digging a bit deeper into metal binder jetting, as mentioned, 4 systems are running. On the upper left, you see the recently set up X1 system, the 25 Pro printer, which has a build envelope of 25 liters. We run 2 Innovant Plus systems and 1 older, simple Innovant system, let's call it like that. We are fully equipped with debinding technology, solvent debinding, catalytic debinding, but also classical sintering ovens and combined with debinding possibilities. 2 very big systems, Elnick systems of 30 and 60 liters, so we can represent the full process chain of metal binder jetting, again accompanied by metal powder qualification, metal powder testing. Just one impression or a few impressions of the big printer, 25 liters of build volume, newly installed at our premises in Bremen. This is a look inside the system. So a big building box, in this case, completely filled with metal powder. This is the depowdering station. So this is not yet automated. It's a glove box where the whole build box is put into and then manually depowdered at the moment. And for those of you who are not yet familiar with the metal binder process itself, a brief introduction into the process. So this process is a cold process compared to the beam.
Klaus, we lost your sound.
Klaus. Okay, George, maybe a reaction.
Klaus, can you hear me? Klaus, we lost your sound.
Klaus. Talvez email. I'm going to send an email. Klaus. Klaus.
I don't know what happened. So
Neither, because
his microphone is on, but doesn't show any sound.
algum problema, Jorge? Should I do something?
I don't know what can we do.
Decline a participant request live transcription. Okay. Ask to unmute.
Professora Paula, se calhar se tentar parar, pedir-lhe para parar, é a moderadora, não é, desta sessão?
Espera. A Margarida tem razão. Continue. Onde é que ele está? Klaus.
We are not listening you.
Klaus, we lost you.
Já experimentou escrever-lhe no chat?
Já.
Ok.
We have lost you. I'm sending him some. I'm sending him some messages. Oh my God, this was going so well. Report. Report what? Aha. Submit. Other. Private. Yes. Klaus. Sanchez, you need to turn this up the other side. Hey guys, sorry about this. I'm trying to find a phone number. Maybe a mobile phone. Klaus. Give me just 1 minute. Okay, there's a phone number here. Yeah, so give me just a minute.
He's not in the meeting anymore. So, yeah, some problem. So I'm sorry for that. So we'll wait some more minutes. Try to fix this.
So I'm reconnecting.
Okay. Because up to now we didn't have any problems.
Yeah. Sorry for that. Sorry for that.
Okay, maybe that's a good idea. I'm at the meeting you now.
Yeah, okay. Yeah, I can see you.
Okay.
I can see you again.
Very good.
Okay.
I don't
Yeah.
know. Can you hear me via the internet?
Let me. Okay. Now we can see you. Okay.
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 Great.
So I'm going to turn my mobile off. Okay. Thank you.
Yeah.
Can you hear me? I can hear
Yes.
you.
Yes, we can hear you.
Okay.
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 So
can,
Dr. Klaus is back.
Sorry. So
okay.
I will try to step in again. So you
Yes.
said 10 minutes ago.
Something like that.
I will.
You can share your screen.
Yes, I was presenting
The metal
IFAM
binder
technology.
jetting.
Metal binder jetting already.
Yes, yes, the process scheme. So we didn't list anything in that slide. Yeah. That's
okay. Okay. So this was the last slide you saw.
We are not listening, not seeing the
Right?
slide yet. Oh yes. Now it's okay. Yeah, that's it.
Okay. So I'll start again with the process description. Okay.
Okay.
Oh, no. Yep. So the video seems to be frozen, at least on my side. Can you still hear me?
Yes, we can.
Okay. So the first step of the metal binder process is to apply a powder layer as with the beam-based processes. So it's a powder bed-based process and a layer by layer build-up. In the second step, a binder is printed into the first powder layer. This binder is then cured by a heat lamp. And everywhere where you have binder in your powder bed, this is one layer of your part. And then these three steps are repeated. So powder layer, printing into the layer, heating the layer. And so layer by layer, you build up your three-dimensional part. These parts are inside so-called build boxes. And the whole build box is put into a curing furnace and the binder is cured. So it's a kind of pre-step on its way to a three-dimensional part. When the parts come out of the curing furnace, you have so-called green parts. So metal powder glued together, stuck together with a binder. And these so-called green parts are then in a step 6, put into another furnace and are debindered. And in the same furnace, they are sintered to either full density or they are only pre-sintered. And during this last step, number 7, we have a certain shrinkage of the parts, so the parts in gray are still bigger than those in black. This is intended. The parts become smaller after sintering. We have two process variants. One is sintering to full density. The other is sintering plus infiltration. I will try to speed up a bit. So with sintering to full density, you have the green state displayed here in the picture on the right. You have the sintered part, which is smaller due to the shrinkage during sintering, and you can polish the part. Here again, comparison of green part and smaller sintered part. And the part displayed here on the right is an infiltrated part, where you have only pre-sintered, almost no shrinkage, and you infiltrate the part with a lower melting material like a bronze, for example. The matrix may be a steel material, and the bronze is then the lower melting material for the infiltration. Generally speaking, we can sinter and use all materials which are sinterable. So stainless steels, nickel superalloys, high-speed steels, and every metal powder which is sinterable can be used for binder jetting. Here's some examples again. And one big difference between the metal binder jetting approach and the beam melting approaches is that with metal binder jetting, we need no support structures during printing. So overhangs do not have to be supported, and the picture on the right, these two pictures represent the same part. On the left, the binder jetting approach, and on the right, the beam-based approach, which has to be supported. That's the big advantage of binder jetting compared to the beam-based processes. So no contact to a build platform, no support structures. The green parts are deposited in the loose powder and can thus be taken out of the powder without a removal of support structures. I will skip this slide. This only represents the usual process chain with my institute's competencies, what we do. The challenge with binder jetting is the sintering step, because sintering is a diffusion driven process and is very much dealing with sintering temperatures. So here we increase the sintering temperature from in 10-degree steps, and you can see the differences here. If we get too hot during sintering, we lose geometry. So to use binder jetting, you should know how sintering works in general. And you should have some equipment for sintering, like special sintering ovens. Makes things a lot easier. I was talking about support structures we don't need. This is not the whole truth, because during sintering, gravity exists as on the whole planet, and the structures get weak during sintering due to the high temperatures, and sometimes you can lose your geometrical accuracy while sintering. So sometimes you have to use even here support structures, or you have to work with so-called setters under your green part during sintering to keep the quality of your geometry during sintering. But you need much less support structures than than for the beam-based processes. If we look at the powder for metal binder jetting, we work with much finer powders compared to the beam-based processes. So we have mainly powders of MIM technologies or used in MIM technology. So we are working with powders below 20 microns. And there we always have a trade-off between flowability of the powder during the buildup of the powder bed and the sinterability. The finer the powder gets, the better it sinters together, so the higher the density of the parts will become, but the spreadability, the recoatability during the printing step might become a challenge. We have done a lot of tests with powder mixtures and have found out that mixing powders, so standard powder plus additional fines, can be a good compromise between green part density, in this case, so stability of the green part, and sintering activity. I won't go into detail concerning this. So the powder has a big influence on the recoating process, on the depowdering and the sintering steps. This is also known from the beam-based processes that the powder has a big influence, but this have to be taken into account to set up the process and to design the parts in the end. The powder quality management is crucial for mass production, if you think of that. The good thing with binder jetting, to mention this shortly, is that we have a very active market concerning the manufacturers of systems. So we have at least 4 manufacturers from the US, X1 Desktop Metal, GE Additive, and Hewlett Packard, who are very active in the market. We have one company from Sweden, which is Digital Metal. So a good market activity, as we also have with the beam-based processes. This makes things interesting and good for the customer. Just few remarks on the current system. So we have one very large system also from Desktop Metal. Here you can see the figures. And one other thing to mention in comparison to the beam-based processes is the building speed. So Desktop Metal, for example, has announced a building speed of 12,000 cubic centimeters per hour. So this is 12 liters of part material being printed in 1 hour. And comparing this to the beam-based processes, they are far behind that. So at the moment, we see a very large interest from industry looking into binder jetting due to these high building speed. These 12 liters have not yet been proven by Desktop Metal, but we are on a good way. So at the moment, I would say we are at about 1.5 liter to 2 liters an hour. We have not been able to test the limits of our 25 Pro system yet, but we are much faster than the beam-based processes. And this is one of the big differences. This is the Digital Metal system, much smaller, but very precise. So for jewelry, for very precise parts, Digital Metal has shown a lot of very nice parts from their systems. X1 offers small systems for material development, and the 25 Pro, which is a production system, so already interesting for industry. And under development is a system called 160 Pro with a build box of 160 liters, also with a very high build speed, just to give you an impression of what is offered by the system manufacturers. This is the HP system, also high build speed, different printing approach. They use thermal print heads instead of piezo print heads, but Hewlett Packard is a very experienced printer producer, so also industry is looking into this technology. GE is active internally, not active in the market itself, but has also announced their systems to step into the market quite soon. To conclude, with binder jetting, we have, in comparison with the beam-based processes, we have a cold printing process, which ends with very low residual stresses, so no cracks from the printing step in this process chain. We have no connection to any build platform and not that much support structures to be removed. The surrounding powder can be recycled, so the powder which is not glued together. We have a quite low roughness, and the roughness is almost independent of the build angle. So the roughness on the top of the part is comparable to that at the side of the part. And we have a print head bar, mostly allocated with several print heads, and by this we have a very high build speed. This is a table comparing the beam-based technologies, also direct energy deposition with metal binder jetting and some other technologies. All have their pros and cons. Binder jetting is interesting for real production, so not for prototyping, filling the gap between, let's say, 1,000 parts a year and 100,000 parts a year, where a mold would make sense already. But it's not, of course, not solving every problem of additive metal manufacturing. It's just another variant of the processes. And here again, a comparison of possible build rates. So binder jetting is indeed much faster than all the others. This is the reason why industry looks into it very deeply at the moment. Just a very short remark on a workshop on these so-called sinter-based AM technologies. Last week we had our second workshop, very successful, 70 participants, very good presentations, and of course people were lucky to meet themselves face to face again. And this will be repeated next year in September. And with this, I'd like to end my presentation, and I'm sorry again for losing the connection. And I'm open for questions if we have time. So thank you again.
We have time. Thank you very much for your very interesting presentations. The presentation. We have time for questions. If are there anyone that wants to put some questions to Klaus? In the meantime, I can ask you one question, and I want to listen your feeling about this. So because we are considering this technique that is based on a binder, we need a post-processing to remove this binder and also the sintering. So because we have these two stages, so it's more difficult to control parts distortion and also the shrinkage. And also about the questions related with environmental problems because of this binder. So what is your feeling about these problems?
Yes, a lot of points. Let's start with the general feeling. So with binder jetting, the approach of first right time is still a challenge because we still not have a simulation tool to really be able to simulate the shrinkage and distortion during sintering. This is under development. Last week we saw many interesting presentations of simulation approaches. So this is, of course, one very important hurdle we have to take with the whole process to be able to simulate it. The environmental problems with the binder are not that severe, I would say. So there are two big binder families, I would say. There are water-based binders and solvent-based binders. The water-based binders have the challenge that they can't be used with corrosion corrosion attractive material. So with stainless steels, this is no problem, but with some tool steels, this causes immediate corrosion. So there you are forced to use solvent-based binders. These binders are completely driven out during the debindering step inside your oven at very high temperatures. So we do not have problematic residuals from the binder in the end. That's the general remark. And as I said, this technology in general is very close to classical powder metallurgy processes like metal injection molding, for example. Yes. So if you are experienced with metal injection molding and have debindering and sintering equipment, the step is very easy to also implement binder jetting. The differences are there. You have much more binder with, for example, metal injection molding than you have with binder jetting. So the parts behave differently during debinding and sintering in the oven, but metal injection molding would be the process which is closest to metal binder jetting in general.
Okay, so I think that we still have a long run or a long way for doing research in this field, and also the simulation can be a very helpful tool in this technology.
Yes, definitely.
So we have another question. Andrea Novolino raised his hand. So please, Andrea, can go ahead.
Hello, are you listening?
Yes.
Yes. Hello, Andrea.
Okay. Thank you for the presentation, Dr. Klaus. I'm not used with binder jet process, but I need to know if does the process need any post-process procedures to introduce the product?
You end with a sintered part. So a sintered surface, for example, it is usually much smoother than a surface coming out of a laser melting process, for example. if you have high quality surfaces for, let's say, gliding purposes, or you have high quality threads, then you would need an additional post-processing step to reach the final quality. This is more or less like you have it in classical powder metallurgy. It depends on your layer thickness and on your printing systems you use. So if you use, for example, the digital metal system, which can print very precise parts, then you might be fine with the part quality coming out of the sintering oven in the end. So this is comparable then to MIM. The digital metal system has the disadvantage that the building box has only a size of 2.5 liters. So it's not for producing many big parts. It's yeah, better to produce a small amount of highly precise parts.
Okay.
Okay, thank you. And how mechanical properties are present in this process? About
so
anisotropy?
This is absolutely comparable to classical powder metallurgy. So full density is a challenge, but we reach densities of 98 to 99%. And for many applications, this is absolutely sufficient.
So that's one of the questions that we have here in the chat is about how do you compare the mechanical properties of binder jetting with powder bed fusion in terms of metals. So from your last answer, it seems that it depends on the porosity of the samples, because that's the main reason.
Yes, of course. Then density is determining the mechanical properties, and above 99% density, you are absolutely comparable, at least with MIM standards, and in many cases also comparable to materials who have been laser beam or electron beam melted. Yeah, depends on the material and on the quality of your process, of course. Binder jetting at the moment is not as far developed as the beam melting processes are, but the big potential is the high build speed, and yeah, time and volume are or can be translated into money in the end. So industry is really looking into this binder jetting approach, and it will definitely find its way into industry for special products. If you take, for example, high carbon steels, which can't be processed with the beam melting technologies, binder jetting is a real alternative to process these materials.
Okay, so you are saying that the speed is the big potential, but when you compare both technologies, we also have this extra stage for this debinder stage. So, and this takes time. So, but you are now presenting another very good point, that is the capacity to process different materials.
Yeah.
Okay.
So as with many of the other AM technologies, there is no technology which is able to process all materials in all build speeds and with all the precision needed. So all the different approaches have their pros and cons, and have their niches. If you take the direct energy deposition, for example, with that you can produce parts of a meter in diameter without any problems. So they are the preferred technologies to produce these big parts, and binder jetting, yeah, is able to produce at high speed special alloys, and will definitely make its way into industry. That's what we see, and that's what we just heard last week, for example, from companies like Sandvik, who are producing tungsten carbide cobalt material based on binder jetting, with very good results, and absolutely comparable to their standard processing routes, with the additional degree of geometrical freedom you gain with additive. So directly printing from the CAD model without needing a tool or a mold to be produced. And there we see many other applications where binder jetting will make its way into industry.
Okay, so this is very interesting, and this opens a lot of opportunities for with this technology for different kinds of parts. Okay,
definitely.
And also from what I understood, you say that this technology has high potential for small parts, because we can print a lot of small parts on the same batch with high speeds and different kind of materials, so it opens a lot of opportunities.
Yeah, not different kinds of materials in one build box.
Yeah, yes, sure.
Yeah, so yeah. Material combination is only possible with this infiltration variant I tried to explain, but yes, we can produce and process all materials which are sinterable, and these are quite a lot. The big or the big bottleneck today is still aluminum. So sintering of aluminum and its alloys is a science on its own that's not really solved yet. So their binder jetting is definitely limited, but all kinds of steels and titanium, for example, copper, bronze, and all those materials can be easily printed and sintered. Those are known material for the classical powder metallurgy. Therefore, we know the sintering conditions, the sintering regimes. It will take some more years until this is, or binder jetting will be present in industry, but it will get there, definitely.
Okay, thank you. We have here another question on the chat.
Yes.
Do you think that binder jetting could play a role in building IM multi-materials part, apart from the infiltration approach?
Not today. This will be a second step. As with all the powder bed based processes, this is a real challenge. Also with LBM, we do not really see multi-material solutions. There are colleagues on their way looking into that. It's a special challenge here, because you have to find two materials which have the more or less the same sintering behavior. So combination of materials with sintering is possible. We have done this with MIM approaches. It will take even longer to be able to offer multi-material situations. At the moment, we only have the choice of this infiltration idea.
Okay. All right.
So there, the beam-based technology are further in their development.
Can I ask a question, George?
Yes, Paula, please go ahead.
Klaus, my my question was a comment more related with the application of this technology in the industry. Are there already industries using this as a manufacturing process on a regular basis? Or what do you think are the biggest limitations?
It's not really present in production yet. So last week we had a presentation from Sandvik, who produces their special cutting tools from tungsten carbide cobalt materials, so hard materials. We have GKN, who are very much involved.
Oops, we lost you again. Dr. Klaus, we lost your sound.
In establishing a production process with binder jetting. Challenges are the simulation, which has to be developed or has to be improved, but this is not distortions or shrinkage rates. Sintering is a very complex process, not easy to simulate. A lot of work is ongoing. And the second big challenge is the automated depowdering. We do have the big advantage to not have to build on a platform, so we don't have to EDM the products off a platform or remove that many support structures as with the beam-based technologies. The parts themselves are lying in a loose powder bed, but still this powder has to be sucked away or blown away. And this is not automated yet, because there we have the challenge of the relatively brittle green parts. So green part stability improvement is one vital step we have to go to be able to do this automated depowdering. There are ideas, there are test rigs we have seen so far. This will have to be developed further. So it will take us another at least 3, I would rather say 5 years, until we really see a binder jetting being integrated into production in industry.
Okay,
but nevertheless, it's fast, it's able to process special materials, and it will find its niche in industrial production, I'm quite sure.
Thank you very much.
It's more or less the same we had with the MIM technology some decades ago. It took some time to establish this, and binder jetting will see more or less the same development, I'm quite sure.
Yeah, I in that point, I share. Yes, we are. Yeah.
Can't hear
yes.
you. You're not moving.
I'm moving. Yes, we are
I'm
moving.
afraid we have lost connection.
Jorge, o Jorge está aí, não está?
Sim, estou.
Nós estamos todos aqui. O Klaus é que de vez em quando vai saindo, não é?
Yeah.
Portanto,
we lost his.
My video.
No, we are still listening, but he's not listening to us.
Klaus, can you hear us? Not anymore.
Oh my God. Are
you still with me?
Yes,
yeah,
we are.
Yes, we are. We are not.
We cannot see you.
And we cannot listen in you.
Yeah. Okay. Mm. It's a pity, right? It was a nice talk.
Yes, yes, it was very interesting.
Yeah. Okay, so George, please don't move. Don't move. So I take the opportunity to say that the next speaker that Professor Jorolino will present, and then after we will have a break for lunch, and we will return at 2 p.m. Okay. So George, I think that maybe we move on.
Yes, yes, we'll move.
Okay, thank you.
So thank you very much for all that attended this session about AM of metals with the binder jet technology. So we have 76 participations in this session. So which I think it's good, and we have also a very good interaction with our speaker. So thank you very much for you attending, and also for the questions that you raised to our speaker. So I learned a lot with this presentation. That it's a pity that we had this connection problems, but anyway, I think that
Klaus is coming. George, Klaus is coming.
I'm back again.
Klaus is coming.
So I was like saying that it was a very interesting presentation, and that I learned a lot. And also we have the participation of our public, and with some questions for you. So thank you very much for your participation in this our workshop on AM applications and innovations. And I hope that we will keep in contact in the future, because this is a very promising technology. But you have not just this technology, but you are working in other fields, and so I think that we will interact. Not only me or Paula, but also all the ones that participate in this seminar. You send us your contacts in the last slide, and so people can raise you questions, and so
yes.
Thank you very much.
And one of the next EPMA conferences will be held in Lisbon. It was planned for 2019. I'm not sure, or 2020. 2020, yes. Couldn't take place due to the pandemic, and I think it's now planned for 2024 or something. So then binder jetting will have improved also.
I'm sure.
A big jump.
I'm sure. Klaus, thank you very much. It was very nice. Your contribution was really important. I think that in 5 years, we will have other results and other implementation. No doubt on that.
Thanks for inviting me. Have a good day.
Thank you.
Bye-bye.
Thank you very much. Bye. Bye, Klaus. Thank you.
Thank you very much.
Thank you.
Thank you very much. So we will move in our program for the next session or next presentation, that we call it company institution presentations. And we have the Young Ceramics network. And for this presentation, we have Nicholas Summers. Thank you very much for being with us in this seminar. And I'm very curious about what stories do you have to tell us?
Hello, can you hear me well?
Yeah. Yes.
Thank you very much. I'm very happy and honored to be here with you to be able to advertise this great network, the Young Ceramics Network. So I will try to share my screen first, maybe. Yes.
Okay.
So can you see?
It's coming.
Yes.
Yeah. Yes.
Okay.
Yes.
Perfect. Perfect. So should I start? Yes.
Yes.
Okay. So I won't take too much of your time because it's quite late. I think everyone is a bit hungry. I just want to advertise you the Young Ceramist Network, which I'm part of. So I'm Nicolas Sommers, a last year PhD student in the University of Valenciennes in France, and I'm part of the Young Ceramist Network since last August. And typically, the Young Ceramist Network is an initiative of the European Ceramic Society, sponsored by the ICERS and the JEC Trust. So typically, it's a non-profit network which aims to bring all together young students and professionals currently doing research on ceramics. So we receive funding from ICERS and JEC Trust to organize events and to promote networking through the young community of ceramists. And in order to do that and to keep this network alive and active, we have an executive committee composed of 5 very motivated young researchers doing research on ceramics. We are supervised by Andras Koznaj, who is the head of Young Ceramist and Training at ICERS, and also by the 2 administrative officers of ICERS, Veronique and Donatella. So why the YCN? So typically the YCN wants to provide a platform for young researchers to build their own professional network. So you can have a lot of benefits from us. Actually, you can have funding and to attend professional events, to make contacts, to form links with other young researchers, but also with industry. You can benefit from these meetings to exchange ideas and also work experiences, and to get information about funding, job opportunities. If you need some kind of equipment, you can ask in our groups. It's a very huge community, so it's a very useful tool for young researchers. And the main goal is always promote research and innovation in the field of ceramics. So you can find us on different social media, but we have also a website called youngceramics.eu. And you can find on this website all the activities we are doing currently, and also this great map. We are very proud of this map, because on this map you can easily find all the location, all the institutions doing research on ceramics, where there are some young researchers involved. So it's very easy to find a location or an institution if you want to do a collaboration or to travel and maybe spend some months in other institutions for your research. So I encourage you, if you don't find your institution on this map on the website, I encourage you to contact us and to send all the information of your institution, and we can add this on this great map. So you can see we are mainly present in Europe, but we are starting to have some connections in the US and also in Asia. So we are very proud of this map. I think it's very strong tool for the young researchers. So the YCN is also present on social media. So we have a LinkedIn group with now more than 900 members. So it's a very huge community to exchange ideas and ask questions about conferences, funding, everything. We have also the Facebook group, which is the main social media platform, let's say. So we are close to 1,000 members now. So again, huge community to share information, to ask questions. So to be a member of the YCN, you just have to go to this group and to add to be member, and you will be automatically a member of the YCN. So it's quite simple and easy and free. So I encourage you to join us to extend this huge network. We have also a Twitter and Instagram account to be present almost everywhere for the young community. So the YCN have different activities. Actually, we have a newsletter. We organize a photo contest. We also organized last year a special issue in open ceramics. We also organized different webinars and a workshop. And we like to keeping some partnerships with, for example, the American Ceramic Society students and young, with Australia, with also Chinese ceramists, and also the glass community. So we try to have a big network with a lot of connections. So typically for the newsletter, this newsletter is read by 11,000 people with the database of eSource. So it's a very strong tool to share information and to maybe focus on certain points or certain research. And in this newsletter, we have a special section called "From the Research to the Industry Spot." And in this session, we like to highlight the work of young researchers in academia, but also in industry. So if you are interested, you can send us an abstract to, describing your research, making some advertisement of your work, of your company, and it will be a pleasure for us to put it in the newsletter and advertise your research. I think it's a strong tool to make to have a good visibility of your work and maybe create some new collaboration and find some positions maybe. So do not hesitate to send us if you want, send us an abstract or proposal of your research. So last year we received typically more than 30 contributions from different young researchers in the world, from Europe, from Asia, also from the US. So it's a great community. And again, thank you for all the members who contributed to this newsletter. We also organize a photo contest. So typically you can submit and send us your nice micrographs you made in the lab. And last year we received more than 20 micrographs. So it's a very nice, it was a very nice contest with you can see here very beautiful pictures. And of course there are winners of this contest. So here you can find the 3 last winners of the photo contest with special prizes, and they have also the chance to be the new cover picture of the Facebook group. So it's again a very nice opportunity to get some visibility of your work, of your nice pictures. So stay tuned for the next photo contest. I think it will start by the end of the year, so we'll have more information at that time. We have also the chance to work with Open Ceramics to organize a special issue dedicated to young ceramists, actually, last year. So this special issue was called Young Ceramists in the Spotlight. It was only dedicated to young ceramists, so typically PhD plus 10 years. So it was, again, a nice opportunity for young researchers to publish for free in a very nice and famous open ceramic journal, open access journal, sorry. And we had a lot of success because we received more than 70 submissions to this special issue. So it's one of the most successful special issue of the Open Ceramics. And we will give soon the Best Paper Award to the best paper submitted in this special issue. So again, thank you for all the people who contributed to this special issue. In these difficult times, we wanted that all the ceramic community, especially the young ones, stay connected all together despite the hard conditions and the fact that we cannot meet all together. So we decided to create some webinars. So we started last November, and we made 10 webinars with around 20 speakers and more than 500 participants in all these webinars. So it was a success. We talked about different topics from advanced ceramics to glasses, also additive manufacturing, and also sustainability tips for publishing papers, also get funding. So we join also academia in industry in these webinars. We receive speakers from Asia, America, and Europe. So people from all around the world. And we also collaborate with different networks, for example, the American Ceramic Society and the International Year of Glass 2022, to create these nice webinars with the most interesting topics possible. We will continue this series of webinars, but we will start, I think, in the next month. We start with new webinars, so you can stay tuned for the next ones. So here you can see some nice webinars, some titles of the webinars we organize. So we have the chance to receive very interesting and famous experts. For example, Professor Richard Todd, who is the editor-in-chief of the European Ceramic Society Journal, and also the president of eSource, John Biener. So thank you again for all the speakers who participate to our webinars. And after all these webinars, we decided to organize an online event in June, which was called Pitch Me Your ID. So it was a pitch contest, actually. So every young researcher who wanted to take part of this contest had 5 minutes to pitch their idea, to defend an idea or research to jury members. And there were like some awards also, money prizes, but also free registrations to the main eSource conference the next July. And for these webinars, we receive different experts talking about how to make a good pitch, how to speak like in tech talks like TED, tech show. And also we receive Dr. Peter Mitchell, who talk about how to create a good CV. And we have also the chance to receive Professor Paula Villareño to talk about philosophy of success. So again, thank you, Professor Villareño, for your presence at this event. So it was quite a success because we received around 80 people from a lot of different countries. So it was a very great event. We organized it with Gadathon, so it's quite interactive. So it's almost in a real conference, but still online. We can connect and talk and have like a coffee break, like online coffee break. So it was very, very nice for all young researchers to meet and share ideas and experiences. And again, congratulations again for the 4 winners of this pitch contest who received money and also free registrations for the next ESERS conference. We have winners from Europe, but also from Brazil, so you can see how big is the network all around the world. So again, thank you for this event. To finish my presentation, I hope I convince you to follow the YCN, at least join our Facebook and LinkedIn groups to see all the information we share. And it's not because it's called Young Ceramists Network that it's not it's forbidden for less young ceramists, so it's open to everyone. Don't hesitate to join us. It can be nice that also older researchers can join and share experiences and talk about the careers, or they manage to get the position and everything. So I think it can be very useful for the young generation. So do not hesitate to join us. I always say that science is a sport team, so you can go further without help and collaboration. And I think the YCN is a very strong tool for that. So I hope you will join us very soon. And thank you again, and enjoy this great workshop on additive manufacturing.
Okay, Nicholas, thank you very much for your very interesting presentation and motivation also for us to join this JIX Trust. We will have a short video about this JIX Trust, and after that we can ask you some questions and some interactions from all the participants that we have here in this session. So Joanna, go ahead. Thank you.
I think we don't have the sound.
Yeah.
You don't have sound.
Não sei o que é que se passa aqui. Está unmute. Joana está unmute. Ok. Continua unmute. Mas eu ouço os meus. Não, João. Onde é que está?
Okay, I'm sorry for this sound problem, but
Yeah.
we'll distribute the link, and you can access
Yeah.
the link and watch again this movie.
Yeah.
So Joanna shared already.
We are using. We are using the internet.
Yeah,
YouTube platform, right?
Vimeo.
Are there anyone that wants to ask some question to Nicholas? Some doubt? I think that the presentation was very clear, and also this video also shows us some interesting information. So I think that what we have to do is to join, to join and we are working on this field, so we should join your association and participate. I don't know, Paula, do I have to,
Yeah, sure.
to
Thank you
close
very
the
much.
session of this morning?
Thank you very much. I have a little bit of echo here. Give me just a minute. Okay, I think not. George, thank you very much, and Nicholas, thank you very much. It was really a very interesting presentation, no doubt on that. And I fully agree with Professor Lino, everybody should join. It's only advantages, there are no disadvantages, so why not joining and contributing to this force of nature that is materials, right? There is nothing in the world without materials. Ceramics, metal, plastic, polymers. George is laughing. That's composites, you know, it's impossible to live without materials. So I think, Nicholas, you are doing a great job. I will do a job for this network from my side, because I do believe in all of these things, and working all over the world is an amazing experience. So well done. Thank you very much for being here.
Thank you. Thank you.
So George, thank you very much for your job. You did a great job. I think we started quite well this morning. Now we will break, and 2 p.m. Lisbon, London, Dublin time, we will be back. Okay. Thank you. Thank you. Bye-bye.
Thank you. Thank you all.
Thank you. Bye.
previously on XGen Nanoparticle Jetting. To a new era in metal additive manufacturing. Now, it's time to demonstrate how XJet leverages the same nanoparticle jetting, or NPJ technology, for ceramic 3D printing, using our new Carmel line of AM systems. Unlike existing approaches, XJet's NPJ is a highly versatile and scalable inkjet-based technology. NPJ uniquely empowers the manufacturing of high-quality ceramic parts of virtually any design with superfine details, all in a simple and safe process. So, how does it work? Ceramic materials, packaged within convenient cartridges, are easily and safely loaded by hand into the XJet Carmel AM system. With no need for a powder or liquid vat, the Carmel system uses only the materials required. Suspended within our unique liquid formula, nano-sized particles are jetted from thousands of inkjet nozzles. These nanoparticles, of various sizes and shapes, are randomly distributed to allow for natural packing and high density. Liquid droplets containing either ceramic model or support materials are simultaneously deposited onto the build tray in an ultra-fine layer. The ceramic part builds up as the tray descends with each pass of the inkjet print heads. After printing, the support component, made of a soluble material, is easily disintegrated, allowing for fast and clean support removal. The non-UV sensitive materials utilized by NPJ technology enable simple single-step sintering. Our versatile NPJ technology empowers the rapid production of ceramic parts with superfine details, unprecedented safety and simplicity, and unrestricted geometries. XJet nanoparticle jetting technology and the Carmel line of AM systems, redefining ceramic additive manufacturing. Imagine cars and planes becoming lighter and more fuel efficient. Dental restorations more functional and long-lasting. Imagine spare parts printed on demand within minutes at your local hardware store. Introducing LSPC. With the affordable Nexa 3D printer.
Já temos aqui, temos tudo preparado, vamos só aqui aguardar mais um bocadinho à espera que se junte toda a gente e dentro de pouquíssimo tempo iremos dar início aqui ao nosso webinar. Obrigado.